Good morning. This is the first of two talks on the same topic. The second one will be given by my collaborator, Zhao Shengzhen, immediately after this. Now, when Yang-Mills theory was first discovered 60 years ago, people immediately recognized its significance. I did not myself because I was too ignorant at that time. But it was unclear at that time what physics context it should be applied in. Now, 6 years later, Yang-Mills theory, as you all know now, is enthroned as a theoretical basis of the standard model of particle physics. And that means essentially all known physical phenomena apart from gravity. And this standard model can claim to be the most successful theory ever, given the range of phenomenon it covers, and also its resilience in surviving the many stringent tests it has been subjected. But at least to the fastidious theoretical mind, there's something still missing in this beautiful picture. In particular, there's no understanding of the origin of the Higgs boson needed to break the electroweak symmetry, nor of the 3 generations of quarks and leptons needed to fit experiment. Neither is part of the Yang-Mills structure or has any other theoretical explanations. Besides, of course, there's some ominous clouds on the horizon. For example, the strong CP problem, the right-handed neutrinos, dark matter universe, etc. And of course, linked to gravity, that's still missing. To address these shortcomings of the standard model, if indeed there are shortcomings, the most popular approach is to keep Yang-Mills structure intact, as usual, but enrich the superstructure. One, for example, you can enlarge the gauge symmetry beyond the usual SU3 cross SU2 cross U1, things like grand unified field theory, supersymmetry theories, etc. Or you can enlarge the space-time dimension beyond the usual 3+1, like Kaluza-Stein theory, etc. Or you can enlarge both in superstrings, superbrains, etc. This approach to enriching the standard model give grand vistas of things to come, but they're much less successful in giving solutions to the immediate problems that we're asking about, say, the Higgs field and generations, etc. For example, the SUSY models, supersymmetric models, instead of reducing the parameters in the standard model, have usually 100 parameters or more. So one may think it's probably worth trying another approach to address this simple but down-to-earth problem about the parameters. So one thing that we have suggested is to keep the gauge symmetry as the usual standard SU3 cross SU2 cross U1, and keep space-time dimensions as 3+1, but instead enrich the underlying Yang-Mills structure by framing. By framing, I mean we introduce as field variables the frame vectors in internal symmetry space, in addition, that is, to the usual gauge field A mu and the matter field psi. These frame vectors, or frame-on fields, as you like to call them, are analogous to the Vierbeins in gravity. In that sense, framing might in future facilitate the union of the two theories. But for now, let us keep just to particle physics and see what it gives us. Like the Vierbeins in gravity, frame-ons transform under local gauge symmetry G, SU3 cross SU2 cross U1, but also under global transformation of the reference frame, G tilde is equal to USU3 tilde, SU2 tilde, etc. These are global symmetries, global transformations. And this leads immediately to attractive consequences. A, the Fremont in the electroweak sector is an SU2 doublet, but a Lorentz scalar, the same as the Higgs fields needed to break the electroweak symmetry. And B, since physics is independent of choice of the reference frame, the theory has a double invariance under both G there and G tilde there, where you see the first component, S23 tilde, of the global symmetry is threefold, can play the role of Fermion generations, while SU2 tilde is up-down flavor, and U tilde turn out to be B minus L. Hence, you seem to obtain immediately both Higgs field and Fermion generations as result of the framing, and each is given a geometrical significance, which was lacking before in the standard model. Okay, to push further, we need to be more explicit. Explicitly, and that means some ambiguities being settled by minimality consideration in the number of scalar fields to be introduced. We are led to a weak Fremont of the form alpha cross phi, where alpha is triplet in S23 tilde, a global quantity, independent of space-time. Phi is a SU2 doublet Lorentz scalar field, which you can identify with the usual Higgs field. And secondly, a strong Fremont of form beta cross phi A tilde, where A tilde goes 1 tilde, 2 tilde, 3 tilde, 3 copies of it, where beta is a doublet in SU2 tilde of independent space-time, global quantity again, and phi A tilde are 3 colored SU3 triplet Lorentz scalar fields. In other words, we're saying that the Fremont representation is 3 plus 2 cross 1 in G, a 3 tilde times 2 tilde times 1 tilde in G tilde. Suppose we accept that, then as usual, the three-level mass matrices for quarks and leptons will be given by Yukawa coupling of the Higgs scalar field, where you substitute for the Higgs scalar field the vacuum expectation value. And here, the Higgs scalar is replaced by the weak Fremont above. Now, given extra factor of alpha, you remember the weak Fremont field has this alpha factor there. And so this alpha appears in the master matrix as well. As a result, we obtain the master matrix for any quark or lepton, which can be written in a simple form like this, just by relabeling the singlet fields. Where alpha, the Fremont, is universal. It comes from the Fremont. It doesn't depend on leptons or quarks it coupled to. And only the coefficient MT depends on the Fremont species. T is, for some reason, used to denote Fremont species. Now, this mass matrix is nice in the following sense. It's only one massive generation because it's factorizable. It's rank 1, only one massive generation, and zero mixing. And such a mass matrix has long been coveted by phenomenologists as a starting approximation for the flavor problem. As long ago as 1978, Fritsch and Harari suggested such a mass matrix. You see, it is good in the sense that for one massive generation and two are zero is a starting point, if you like, of the mass hierarchy for fermions. And zero mixing is actually a rather good approximation for quarks to start with. And this is what they worry about in those days. The question now, of course, what happens above the tree level? And this, I think, is where the frame starter model starts to give more powerful results. Because of the double invariance under both G and G tilde, the action is much constrained and allows some radiative corrections to be calculated. Second, since the strained Fremont is both colored and dual colored, correction by strained Fremont loops will change the orientation of the strong vacuum in generation space. And this change depends in general on scale, and hence induces a mu-dependent rotation on alpha in the Fermion mass matrix. Notice that the Fermion mass matrix remain of the same form, vectorizable form, although alpha now rotates because of renormalization effects from the fermions. We call this scheme R2M2, a rank 1 rotating mass matrix. And we have spent some years studying this rotating mass matrix simply for phenomenological reasons. It's nice in the following sense. It gives automatically mixing between up and down states, a non-trivial Ckm matrix for quarks, and neutrino oscillation for leptons. Second, it gives hierarchical mass spectrum for quarks and leptons. Dramatically speaking, it seems that the mass of the heaviest generation is leaking because of rotation to the two lower generations. And third, also quite interesting, it gives a solution to the strong CP problem, transforming the theta angle in the QCD action into a non-zero Kobayashi-Moskva phase in Ckm matrix. I don't think you need, maybe I should remind some younger people what this strong CP problem is. In QCD, gauge invariants actually admit an extra term, which is CB violating, coming from topology, basically instantons, and can have arbitrary coefficient called theta. Theta can be any value. And that would mean that strong interaction with CP violating. Well, of course, we know it is not, because, say, it will lead to neutron dipole moment, which is very large. And present experiment would say the theta is as small as 10 to the minus 11, something like that. For some reason, nature wants to have theta equal to 0. So this is called the strong CP problem. I won't understand why theta should be 0. But in this particular case, there's a solution to the problem in which the theta is transformed away into this Kobayashi-Moskva phase. A brief explanation of the previous conclusion for R2M2 mass matrices. Take, for example, the Ckm matrix. The element VTB is actually just T dot B, where T is the state vector in generation space of the T quark, and B is the vector, state vector in the B quark in generation space. For R2M2, T and B are the values of alpha, this rotating vector alpha, at respectively mu equal to mt and mb. And since mt is not equal to mb and alpha rotates, obviously it means that T is not aligned to B. T dot B is therefore not equal to 1, or VTB is not equal to 1, which is mixing. Second, for example, for U-type quarks, T is alpha, as you said already, and mu equal to mt, and C, being an independent state, is orthogonal to T. So it has 0 eigenvalue at alpha equal to mu equal to mt. The mass of mc is measured at mu equal to mc, and therefore, when alpha is not equal to T, it has non-zero component in C direction and give a mass to mc, which is not equal to 0. This is what we're saying as leakage before. And 3, reason why one can solve the strong CP problem in this way is that R2M2 has 2 0 eigenvalues, every value of mu. One can therefore perform a chiral transformation in these directions where the eigenvalue is 0 to eliminate theta angle in the QCD action without making the mass matrix complex. An effect of this chiral transformation is carried by rotation to other scales, and this gives the Ckm matrix a CP violating phase. So these are some brief explanation of those 3 results. Now, any R2M2 scheme will give the above result D1, D2, and D3, that is mixing, mass hierarchy, and CP violation. But the details will depend on the rotation trajectory, that is how alpha rotates with mu. Now let us see then what the frame standard model we're proposing has to say about this trajectory. Now we recall first that alpha is a global quantity with no gauge interactions, and therefore is not subject to radial corrections itself directly. But it's coupled to a strong vacuum, and that rotates, alpha rotate also. Now the vacuum rotates can be obtained by studying renormalization of any quantity which depends on the vacuum. So let's focus. Historically, we focus on Yukawa coupling with strong frame bonds. By studying one frame bond loop correction to this coupling, the renormalization group equation is derived, and hence the rotation equation for alpha. The implication of the rotation equation is divided into two parts. First of all, shape of the curve gamma traced out by alpha on a unit sphere, alpha unit vector, so it goes on the unit sphere. And second is a varying speed with respect to mu, at which gamma is traced by alpha. The shape of gamma is a consequence most just of the symmetry in the problem, and depends on a single integration constant A. I'll show you what it looks like in the next frame, but let me remind you briefly that, of course, this gamma can be described using the Frenet formula that our chairman mentioned yesterday. So there's the torsion, there's curvature of this one dimension, of this space curve on a sphere in this case. Now, in this case, because on the sphere, torsion is 0 and normal curvature is 1. So only the geodesic curvature is variable. Okay, so we look at this renormalization equation obtained from the frame bond loops, and they look like these. Almost look like a section from the protein. There's even an inflection point there at that point, and it goes like that. As that is mostly just a consequence of the symmetry remaining in the problem. Notice one thing, there's a very sharp bend of the curve around here, but it's smooth off, and eventually, even there's an inflection point there. So the geodesic curvature changes sign there. As you see, there's some physical consequences from this. Just from the shape of the curve obtained in this way, they come to some interesting consequences. First, you notice that these elements, VU, B, VTD, which are these two elements in Ckm matrix for quarks, and also these two elements for leptons, there and there, they are small compared with others, simply from the fact that torsion is equal to 0 for this curve on the sphere. Secondly, these elements, Ckm elements, this one and that one, I guess, yes, are very much larger than this one. That's because geodesic curvature, as I told you in the curve there, has a very sharp bend. So locally, the geodesic curvature is very high there. And this is what is giving this much bigger than this. However, when you go further away, geodesic curvature goes down, becomes smaller, and these are now of the same order. But the quarks being higher in mass and they were up. The quarks are here, and the leptons are more or less there. Okay, but this is a rather interesting thing. We never expected ourselves. The geodesic curvature changes sign, that is beyond the inflection point. And this implies, though not so obviously, that mass of U is less than mass of D. From the leakage, you can calculate that, and you find that the mass of U is less than mass of D. Now, this is, of course, a rather crucial fact that makes the proton stable, without which we won't be here. But it's a result very hard to imagine at first, for us at least, hard to understand, because for the heavier generations, it's the other way around. MT is very much heavier than the MB, and MC is very much than the MS. But because of this inflection point in the curve, it turns out that MU is less than MD. Luckily, otherwise we won't be here. Next, from the renormalization equation, you also know the speed of this curve gamma is traced. There are other information, more detailed information, I think that the next talk will tell you about. But here, we just note that there is a fixed point for alpha at mu equal to infinity. Meaning the rotation will start very slowly as you lower mu from infinity, but we accelerate as mu is lowered further and further. And these also immediately lead to the following results. One, since lower generation masses come from leakage through rotation and will therefore increase the rotation speed, it follows immediately from MT greater than MB greater than M tau that MC over MT, the leakage, is less than MS over MB is less than MU over M tau. And this agrees with the experiment with the mass ratios measured are respectively this, and that. Second, when mixing also comes to rotation, increasing speed. So simply from the fact that M quarks are larger than M leptons implies that mixing for quarks is generally smaller than for leptons. This again agrees. You see, mixing angles, so they are generally larger than for quarks. This is done already. And three, since the quarks are relatively heavy in mass with the rotation slow, you can therefore make small angle approximations to the rotation, from which you can actually get an approximate formula for the Yau-Skok invariant measuring the CP violation of the Ckm matrix of the simple form this. This is only an approximate formula. And for theta of order unity, this is of the same order experimental value of J 2.95 times 10 to the minus 5. And this comes from just basically that there is a fixed point at infinity for the rotation. But actually, one need not stop with these qualitative predictions because you have already rotation equations. So we try to calculate things. True, the equation depends still on a number of unknown parameters, 7 in fact, but they can be fixed if you're willing to inject some experimental information into this, and then to use this information to calculate the rest. Essentially, what the normalization group equation derived in this model does is to replace 17 of the independent parameters of the standard model by 7. So you're able to fix the 7 parameters. In fact, we're able to fix it for only 6 pieces of data. Then you can calculate the values of the other 17 of the total 17 physical quantities appearing as M as empirical inputs. Of these 17 parameters, independent parameters of the standard model, only 12 have been measured experimentally. And the values calculated agree quite well with this thing. The detailed result, I think, will be reported by my collaborator in the next talk. And I shall leave you to judge its significance for yourself after her talk. But whatever its significance, it seems that there's not much difficulty in reproducing existing data by the frame standard model with the remaining freedom in the equations. But what eventually proves the theory is, of course, not the reproduction of known results, but prediction to be tested against experiment. Unfortunately, predictions in FMM are rather hampered by the lack of understanding how to calculate in general when the mass matrix rotates. The method we have used in calculating masses and the mixing angles are only patchy, only applies to single particle quantities. But you want to make more predictions, you need more general rules, and one has not been able to derive those. There are 2 tentative predictions stand out that we were able to identify, and both concerned with the Higgs boson decay. First, the Feynman mass matrix is obtained from Yukawa coupling. If alpha rotates in the mass matrix, you rotate in Yukawa coupling too. And this suggests that the branching ratio of Higgs decay to second generation fermions, such as mu plus mu minus and C plus C minus, are much suppressed compared with the standard model predictions. Thank you. H2, there can be flavor-violating decays, such as H to tau mu, with branching ratio at the 10 to the minus 4 level. Experimental sensitivity is still about 2 orders away from detection of this effect. In fact, there is actually a quoted deviation from CMS of a very small 2 sigma deviation. In any case, too large to be explained by this at the moment. Secondly, due to double invariance of under G and G tilde, the self-interaction potential for fermions is known, and we can actually calculate the mass matrix of the Higgs bosons as well. And this reveals that the Higgs state, the normal Higgs state, will mix with several strong analogs. The details are yet unknown, but this mixing can give rise to decay deviation from the standard model. And Taichung Wu may like to know about that, but we do not know the answer. So the Higgs to gamma gamma may be changed by this mixing. But what is potentially most intriguing is how the strong fermions will manifest themselves. The answer, unfortunately, is not obvious, and at present only speculative. But it seems to us that presumably present in hadronic matter, they are not easy to produce in jets. They may combine with one another by color SU3 confinement to form hadrons, but these may not have usual strong interactions. And these hadrons, new hadrons, will also have rather little interaction altogether with ordinary matter. We're therefore now toying with the possibility that there might be a new constituent to dark matter. It may help to answer partially the question that Professor Yang considered the major question facing us, the next level of understanding. Although these are just speculations, maybe just an exercise in imagination, but since some of the parameters are known from the calculation that Zhao Zhangjiang will tell you, there may be a chance of us to look further at these things and see whether any of these are substantiable, refutable, or not. Thank you. Sorry?
You have a picture of
the curve, yes.
Yeah, so elaborate on the meaning of those curves.
Oh, I should have said that. There are a number of curves. You remember this curve depends on one parameter, integration constant. And these different curves are for different values of the integration constant. And the smaller the value of this integration constant, since I haven't told you what it is, it doesn't matter. But you notice that some smaller values of this parameter A, the curve becomes sharper and sharper bent, eventually become a kink, of course, at A equals 0.
The question is, what is the equation that determines the shape of these curves?
I think Zhao Zhangjiang will tell you the exact equations. It is the equation derived from one loop, one Fermion loop normalization of the Yukawa coupling of the strong Fermion. Right.
Thank you.
Well, from point of view of the differential geometry, you say that your internal space is curvilinear. What kind of manifold is?
Sorry.
I say that you say about frames, so it
Yes.
means that your internal space
Yes.
is curvilinear. It's not plane as in
No,
Yang-Mills.
no.
So what is this manifold?
It is SU3, SU2, and U1. It's the gauge group. Actually.
Just the group itself.
Yes, the group itself, yes.